let's look at an example, and we simplify this by not showing the SSA work list. Well, in a way, both work lists are empty from the beginning, and we start interpreting the program in the start vertex. So we do this and add the edge from 0 to 1 and take out and visit, we take out that edge and visit vertex 1 and interpret all the instructions there and conclude that B0 is not equal to A0, so we will add this edge and interpret all instructions in vertex 6 since it's the first time we visit vertex 6. When we come to this phi function, we don't think that this edge is going to be executed. So we ignore A3 and A2 will be get the value of A0. And then we continue and this will not be 11, so we add the edge from 6 to 7. And not much will happen there, but we continue and A3 is 4, so we add the edge from 8 to 6. Now we only need to reinterpret the phi function since we have already been in this vertex, and well, we do that and see that the A0 and A3 are different constants, so A2 is not a constant at all. Therefore, the value of A2 has taken a step down from constant to non-constant, and we need to reinterpret, re-evaluate all instructions which are executable and use A2. It's this instruction, and A3 will also be non-constant, which means we have to add both of these edges, and we have already had that edge, so we add this edge. And well, we interpret this in the similar way, and well, we can go fast forward, I should say, and we will eventually get down here, and A8 is not a constant. This is all that happens during the interpretation. This vertex can be removed, and of course this conditional branch, so we can just branch there. Okay, so that was that. When we have an equality or inequality test, then we can improve the algorithm. Actually, this improvement is mentioned in the paper from 1991, where the algorithm was published. So we can insert, A must be 44 in the else clause. So we can insert A equals to 44 or represent that in some other way in the code. And then we can evaluate this. Another simple extension is the following. The algorithm does not think that C is a constant. This is very rare to find code like this. So it's probably not worthwhile to implement it. Actually, I couldn't resist implementing it, and it was used like a handful of times in millions of lines of code. It's very trivial to implement, but as a general rule, if an optimization is not useful, it should be deleted. For two reasons. First, it takes time to execute. And second, it can include bugs. And there is a somewhat famous example of that. there was an optimization which was almost never applied in the Bell Labs Fortran compiler. And once, after a few years, it was invoked and found something to optimize, but it was buggy. So the programmer who got this was obviously confused and didn't think it was due to the compiler. And the bottom line of this is that compiler optimizations, they should be used a lot. Otherwise, they should be removed.